discussed a bit classical solutions in connection with the millennium problem and all the difficulties in finding global classical solutions to Navier-Stokes equations. And then I introduced the class of Leray-weak solutions. In dimension 3, and those are nothing but distributional solutions in the energy class. L2 at infinity time, L2 space, intersection, L2 time, H1 space. And I didn't prove the result, but I commented a bit on the strategy of proof. The result by Leray says that given any initial condition U naught in L2 and F in L1, L2, we can always solve within the energy class. And this is our first class of weak solutions. The other class I'm going to mention is the class of Udovich solution to the Euler equation. I'm going to introduce it in a second. But I want to comment a bit more about the uniqueness and no uniqueness problem within the Leray class. I mentioned that this is a very old open question and is still open, so let me state it as an open problem. It's still open when the external body force is smooth or simply zero. So assume that F is 0 and U naught is L2. And the question is there a unique solution? Or if you want, are Leray solutions unique? This is open, still open. The theorem we have is the following. This is collaboration with Dallas and Maria. This theorem says that no uniqueness holds if we add an external body force in the class L1, L2. So there exists an external body force F. Is it maybe too close to my mouth? No? Okay. So there exists a special body force in L1 time, L2 space. Actually, our body force is much better than this. F is smooth in the open interval 0, capital T cross F2. So it's singular only at the origin, at time t equal to 0. I will say something more in the next lecture about the structure of this body force. Such that the Cauchy problem associated to the Navier-Stokes equation with initial condition U naught equals 0 admits two different solutions. So there exists U and U bar, Leray solutions. To an S with initial condition equals 0. Okay, so uniqueness fails at least for very special external body forces. And you don't even need a crazy initial condition in this framework. And next time I'll try to explain what are the main ingredients of proof in this theorem. Here keywords are instability, similarity variables, unstable manifolds. I'll elaborate more next time. Now I want to introduce the second class of weak solution and the second no uniqueness or uniqueness problem I'm interested in. I'll essentially drop the diffusion term, or if you want, yeah.
For the open problem, do you expect uniqueness?
I expect no uniqueness, and there are results, not completely rigorous, but there are numerical simulations, and I mean, there's a very convincing scenario where you get no uniqueness even without body force. So essentially, the picture we have here can be somehow turned into a no uniqueness result with zero body force and a rough initial condition. You try to exchange the role of the initial condition and the body force. The morals should be the same, the heuristic is really the same, and is related to the work of G and Zverak. At the technical level, it is much harder to prove the result in this framework than this. But morally speaking, it should be the same. And the expectation is that the resolutions are never unique. Okay. Yeah. What happens? I don't even know if t is equal to plus infinity. I mean, it's really technical. I would say nothing. So here the key point is the origin. The bifurcation giving no uniqueness is happening at the origin. And I'll show you tomorrow the construction. One of the two solutions is fully self-similar, is defined almost explicitly for every time. The second solution is obtained, is essentially the most unstable trajectory in the unstable manifold associated to the first solution. And when you construct this unstable trajectories, you use a fixed point argument and you have some time of existence, but it's just technical. I expect also the second solution to live forever.
So we don't know if F is smooth after.
F is exactly smooth. F is explicit. Okay, thank you for your comment. As F is explicit and is smooth, is self-similar, and is smooth for every time t positive. And also the both solutions, U and U bar, are smooth for every t strictly positive. One of the two is defined, a priori is just defined up to certain capital T, but it's just technical. Okay. Good. So, let's talk about weak solutions to the Euler equations. So let's see. So again, to motivate weak solutions, I want to start with classical solutions. Again, ideally, even without Laplacian, one would like to build smooth solutions starting from classical solutions, starting from very good initial condition and external body force. All the results we discussed yesterday do not apply in this framework, because most of them were essentially try to understand Navier-Stokes as a perturbation of the heat equation. But now we have no Laplacian, so no way to apply this kind of theorems. But on the other hand, you can take advantage of the so-called vorticity formulation of the problem. Let me write down the equation. I will consider the case n equal 3 in the first part of the lecture, and then let's switch to n equal 2. Let's define, again, I'll run some formal computations. Let us assume that we have some classical solution. We define the vorticity, which is nothing but the curl of the velocity. This turns out to be a divergence-free vector field in dimension 3, and you can if you assume that U solves the Euler equations, you get an equation for the vorticity. It's a very, not easy, but annoying, but still just a computation. And the equation is the following. Let's call it Euler in vorticity. So the time derivative of omega plus a transport term minus the so-called stretching term is equal to the curl of the external body force. So, first observation, here there's no pressure. And there's no pressure because the curl of a gradient is 0. And this equation is nothing but what you get when you apply the curl operator to the Euler equation in velocity formulation. Okay, so the bad non-local term now is not there. Second important observation. Here, the nonlinearity is the sum of two terms. The first is nothing but the transport term. It's just a fraction. The second one is the so-called, oh sorry, I messed up. The second one is the so-called stretching tensor. And, I mean, heuristically, the enemy for well-posedness is the second term, is mainly the second term, because if you are in the right regularity class, here you are just essentially rearranging the vorticity according to the velocity field. You are just transporting. So for instance, you cannot increase LP norms because of this transport term. While the stretching term is able to increase also LP norms. And we can complement this first equation with the inverse of the curl relation. So we want to express the velocity field in terms of the vorticity using the inverse of the curl operator. This is called the Biot-Savart law. It has a very easy expression. The vector field here is nothing but the curl of the Laplacian to the -1 of omega.
Keep it away as far as possible in the next way. If it's not that far, like 5, 10 centimeters, and then if it's too quiet, you can just adjust the volume.
Okay, I think it's much better. Okay. So this is how you express U. I mean, this is just the inverse of the curve. How you express U in terms of omega, and this is an operator of order -1. This is going to be very important in a second. Now, looking at the structure of the equation in vorticity, you expect some well-posedness when you are in a regime where the advection term is well behaving and the stretching term is under control. And we know that if the velocity field, if you have a transport equation and the velocity field is at least Lipschitz regular, then the transport equation is well posed. And if you look at this term over here, if you bound the gradient of U, this term is kind of under control, and it is possible to make rigorous this heuristic, and classical results obtained in 1920 and 1930 by Gunther and Lichtenstein says that the Euler system is well posed. In the class of C1 alpha velocity fields. And here I should add locally well posed. Okay? So if you start with, let us assume f equals 0 for simplicity. If you start start with an initial condition in C1 alpha, alpha positive, unit alpha positive. Then there exists a unique solution solving the Euler equation in a certain interval of time depending on the C1 alpha norm of the initial condition. Okay? And I mean, the key idea is that in this class, the vector field is slightly better than Lipschitz. The stretching term is somehow okay, and all in all, you can solve. Good. And now, exactly as in the Navier-Stokes equations, one might wonder whether this local well-posedness can be extended to global well-posedness, or if you want, one might ask whether a blow-up in finite time might occur. And that's an open question, and it's related to the millennium problem. It's as hard as the millennium problem. Maybe should be less difficult because of the absence of the Laplacian, but still it's a super hard question. Let me put it as an open question. So assume that you have a smooth initial condition, say L2. And assume that f is equal to 0, you can assume f smooth, but let's assume f equal to 0. So we know that there exists some time due to this well-posedness result, there exists some time t star such that the solution is at least C1 alpha up to time t star. And the question is, if you get some solution which is, say, smooth up to time t star. Solution to Euler. Is it possible that the Lipschitz norm or the gradient of U blows up at time t star? And this is not known. There's a very deep recent result by El Gindi a few years ago, and it says that the answer is yes if the initial condition is C1 alpha, which is kind of going very close to the solution to this question. So if the initial condition is C1 alpha instead of smooth, then you can get a blow up in finite time. So even within the class of classical C1 alpha solutions, one might have blow up. So it's kind of a very strong motivation to look at weak solutions. And the natural class here, given, if you remember, the energy conservation for the Navier-Stokes equation, gave us the natural Leray class. If you look at the energy balance for the Euler equation, you get the very same class without the bound on the H1 norm, because this depends on the viscosity. So in our framework, the natural class is simply L infinity L2. So the weakest possible and the reasonable notion of weak solution I want to consider are distributional solutions in L infinity time, L2 space. Okay? And this is somehow the mathematical, one possible mathematical motivation to look for more singular solutions. But there's actually a deeper motivation related to turbulence and what is called anomalous dissipation. Maybe I'll comment a bit about that. I'm not able to away from my nose. Okay, so second motivation to study weak solutions is turbulence or anomalous dissipation. Anomalous dissipation is sometimes called zero flow of turbulence, and is the phenomenon of having a uniform degree of dissipation in the Navier-Stokes equation, independent on the parameter mean. So we wrote down the energy balance yesterday, and we have seen that in the Navier-Stokes system, the amount of dissipated energy is given by mu integral of du xs squared ds, right? Because, I mean, this is due to the Laplacian. And the expectation is that, I mean, a priori one would expect that when mu goes to 0, this quantity goes to 0. Indeed, when mu goes to 0, we solve Euler, and the formal energy conservation says that the kinetic energy is conserved in the Euler equation. So if you approach Euler by vanishing viscosity, by sending this parameter mu to 0, the naive expectation will be that this goes to 0, so the amount of energy that the system dissipates decreases till reaching 0. And what you get is some fluid which does not dissipate any energy. But this is actually wrong. There are experiments and simulation showing that in certain turbulent regimes, when you decrease this parameter mu, actually you don't get zero dissipation. You get some kind of lower bound which is independent on mu. In experiments and simulations, the one possible framework is the following. So you pick a solution to an Navier-Stokes equation with external body force. The external body force depends on the kinematic parameter mu. And usually, the external body force is concentrated on a few Fourier modes, like the first 7 Fourier modes. So it pumps in only low frequency energy. And you wait a long time till the flow reaches some sort of steady state. And the physical process is that low frequency energy gets pumped in by the external body force. Then the advection, the nonlinear advection of the system creates small scales. And the diffusion, mu Laplacian of u, is gonna dissipate these small scales. At some point you reach an equilibrium where you pump in, create small scales and dissipate. And what happens is that at this equilibrium, the amount of dissipated energy does not depend on the parameter mu you started with. It's some number positive. This is observed in experiments and actually in the phenomenological theory of turbulence by Kolmogorov. This anomalous dissipation phenomenon is essentially an assumption. It's an assumption of the theory. So you assume that in average, in certain regimes, under certain assumptions, the fluid behaves like this, and then you draw consequences, quantitative consequences on the energy spectrum, and so on and so forth. from the rigorous mathematical standpoint, we essentially have no good examples of anomalous dissipation happening. We have a few examples where you have anomalous dissipation, but the external body force is not so regular. Instead of being concentrated on a few Fourier modes, it's like maybe Holder regular, but with a very small Holder exponent. There's a lot of attempts and a lot of literature in trying to build solutions to an Einstein's equation exhibiting this anomalous dissipation phenomenon. But so far there are no kind of very convincing examples. I don't want to review this literature here. I just want to use this anomalous dissipation and zeroth law of turbulence to motivate the introduction of, again, distributional solutions to the Euler equations. Indeed, let us assume for a second that we have a solution to the Navier-Stokes equation, a sequence of solutions to the Navier-Stokes equations, depending on the viscosity parameter ρ. And we send this parameter to 0. And let us assume that anomalous dissipation happens. So what we get, if we have enough compactness, is a solution to the Euler equation, in the limit, or at least many solutions, it depends, you get at least one, which dissipates the energy. And this is not possible in the class of classical solutions, because you compute and you check that the kinetic energy is conserved. So the framework is the following, let's say, rigorous framework. So let's pick U depending on mu, P depending on mu, and F depending on mu. Family of solutions to the Navier-Stokes equation with kinematic viscosity mu positive. And assume anomalous dissipation. So assume that the link soup mu goes to 0 of the total dissipated energy up to time 1, let's fix a time scale 1. Is strictly positive. And let us also assume that we have some reasonable a priori controls on F and the velocity field. For instance, a uniform L2 bound, maybe we have some slightly better uniform bound on U nu. We can, for instance, assume that F nu is uniformly concentrated on a few Fourier modes. So this sequence is super compact. We get, it's reasonable to expect some good compactness also of U nu, and so we can assume that up to subsequent U nu converges to some vector field U, and the external body force converges to F. And what happens is that UF with some pressure P is going to solve the Euler equation. So the tripod solves the Euler equations. But now let's look at the energy balance. At the level of Navier-Stokes, what you know is that the kinetic energy at time t plus the dissipated energy, say, let's look at time 1, plus the dissipated energy is equal to the initial vorticity plus the work done by the force. Okay, and let us assume that the initial condition does not depend on mu, or it might depend and is super compact. Now, when it comes to the limit, here you get the kinetic energy. If you have some compactness in L2, you get the kinetic energy at time 1. Here you get the kinetic energy at time 0. And here you get some term which is essentially the body force F, the limit of the sequence against U. The only difficult term is the total dissipation, but we are assuming that the total dissipation in the limit soup is still positive, bigger than some constant. So when you pass to the limit, you end up with an inequality of this form. The kinetic energy at time 1 is smaller by this factor epsilon than the kinetic energy you expect, the initial kinetic energy plus the work done by the force. So if we can make a rigorous construction of this very expected zero flow of turbulence or anomalous dissipation phenomenon, we will get in the limit solutions to the Euler equation that dissipate the kinetic energy. And in particular, they cannot be classical solutions. They have to be weak solutions. But actually, there's a very precise statement about the degree of regularity that we need on weak solutions in order to dissipate energy. And this statement is nowadays a theorem, and it has been a conjecture for a very long time, and it's a conjecture by Onsager back in 1968. Let me write it as a theorem. And Onsager, 1968, if I remember correctly, conjecture that if you have a weak solution to the Euler equation, probably with your solution wasn't the terminology used by Onsager at the time, but if you have some kind of solution to the Euler equation in the class C alpha, then if alpha is bigger than 1/3, the solution must be the energy balance holds true. So kinetic energy is conserved. And the second part of the conjecture is that if alpha is smaller than 1/3, then there exist solutions in the C alpha class dissipating the kinetic energy. And I would like to stress that Onsager is not a mathematician, so he was thinking of this theory in terms of turbulence and the physics of fluids, and he came up with this very precise and rigorous statement about the regularity class where dissipation might happen. Nowadays, this is a theorem, but maybe let me show you. Let me motivate this 1/3 with a very, very easy heuristic. Let's move here. So why 1/3? If you try to prove,
So for the second statement, there are assumptions on F2 or
assume f equals 0 in this statement. Thank you for the comments. So again, let me keep assuming f equals 0. Okay. Now, if you try to prove, so what's the standard strategy to prove energy conservation? You pick the equation, You take the scalar product against U, and you integrate by parts. So this is going to give you dt of the kinetic energy. The most delicate term to deal with is the advection term scalar product U itself. It's this one. U dot grad U scalar product U dx. You would like to say that this is equal to 0 because of the zero divergence condition. So that's zero divergence velocity field dot grad something scalar product something. This is usually integration by parts at 0 when you have enough regularity and integrability. Now the point is, as soon as you have a way to make sense of this trilinear term, then you can prove that it's equal to 0. But let's check the structure of this theorem. You have the occurrence of the vector field U, it occurs three times, and you have one derivative. So you can try to distribute one derivative in one of each occurrence of U. And so what you need is to give a meaning to 1/3 of the derivative of U. If you can get some bound, like this is bounded, you are super happy, right? The C 1/3 condition is exactly a way to understand that you can afford this 1/3 of the derivative in each of you. And to make this argument rigorous is very easy. It's not a hard argument. So you regularize by convolution, you have some commutator, and you pass to the limit. And indeed, the first part of Onsager conjecture has been proven like more than 20 years ago by Constantine and Tilly. The hard part of the Onsager conjecture is to build a weak solution in C alpha, alpha smaller than 1/3, dissipating the kinetic energy. And this is actually very recent. It has been done by convex integration, which is the topic of my last lecture, I hope, if I can complete all the other stuff. And after the introduction of the method by Laszlo Svedilidi and Camillo Dell'Ellis, and the work of many people, the conclusion has been obtained in 2018 by ISTA. Okay? So this is a theorem, and alpha equal 1/3 is really the threshold for energy conservation. And I would like to make a comment about uniqueness, no uniqueness. It's not known what's the Holder threshold in order to get a unique solution to the Euler equation. It is expected to be some data bigger than 1/3, but it's not known. Okay? This is one example where we know very well where the energy dissipation and conservation is gonna, what's the sharp range for energy conservation and dissipation, but we don't know what's the correct range for, yeah.
And sorry, for alpha equal 1/3, what happens?
It's not known. I don't know. In the scale of Holder spaces, I think it's not known. But if you look at Bezold-like spaces, probably you can reach well-posedness up to 1/3 if you set it the correct way with the other parameters of your Bezold space. But in the class of Holder spaces, I don't know.
For alpha equal to 1/3, you know uniqueness.
No, alpha equal 1/3, is a very, so the well-posedness result, the local well-posedness result I was talking about is C1 alpha. So here we are like way below this.
So the last thing is, it's
Yeah.
possible that you have one solution and conserving the kinetic energy one dissipating, for example.
Starting from the same initial condition, it might happen. Yeah, I think so. I don't have examples, but yeah, a priori, yes. What cannot happen is a solution dissipating energy and at the same time a second solution which is smooth, classical. In that case, you have a Wickstrom uniqueness principle. All right, I mean, this was just, just wanted to share some ideas related to turbulence and Onsager, but it was just a motivation to study weak solutions to the Euler equations. Yeah.
And so, from a physical viewpoint, what happens with the kinetic energy?
Where does it go? Where does it go?
Yeah. So.
The point is that Euler is not really a physical equation, right? It's just an ideal limit of a physical equation, which is supposed to be Navier-Stokes. What happens is that when you approach this ideal limit, you have this process of creating a lot of small scales, which is due to the supercriticality of the equation, essentially, which was what we were trying to fight against yesterday. And you have this process of creating smaller scales very, very quickly, and even though your viscosity is super small at some point, you have created so many small scales that you are gonna dissipate a certain amount of energy completely independent from the parameter itself. So this is kind of the physical process that is happening. And this kind of phrasing was already clear to Onsager back in 1968. So if you look at the paper, he really writes down statements like this. There is this cascade of energy from big scales to small scales, and this cascade is very, very wide, super quick. Even though nu is super small, in a short amount of time, you have so many small scales that you can dissipate a well-defined amount of total energy. This should be the picture. So this is what I understand of this picture. I hope I answered your question. Okay. Good. So this was, yeah. Yeah. A priori it might happen, yes. I don't have examples, but yes. I'm about to consider the two-dimensional problem where you can phrase the question of conservation of energy and uniqueness. And in that case, it's expected exactly what you are mentioning. What is expected is that there's a huge range of parameters where you don't have uniqueness, but you have energy conservation. So you might have infinitely many, but it's not proven yet. Let me get to this point. Good. So this was a motivation. Now I want to change dimension, n equal 2, and keep studying quick solutions. And dimension n equal 2 is very good because the vorticity becomes scalar. So if you think of a two-dimensional vector field as a three-dimensional vector field with 0 last component, you compute the curl and you get 0, 0, something. That something is going to be like d1, u2 minus d2, u1, where u1 and u2 are the components of the vector field. And this is going to be a scalar. You can write Euler in vorticity. You get the very same equation, but the annoying stretching term, which is the main responsible for blow up in Gilby's paper, is going to disappear. That's the equation you get. And now this equation is scalar. This is called active scalar because you have essentially you are advecting the viscosity, the vorticity omega by means of a velocity field which is active in a sense that it depends on omega itself. And the relation between the two is still the Biot-Savart law, but in this two-dimensional setting it can be rewritten in a slightly easier way. This is going to be the rotated gradient of the inverse Laplacian of omega. And again, this is an operator of order -1. Okay? The first observation is that the transport structure of the equation suggests that the LP norm of the vorticity should be conserved along the evolution, at least when f is equal to 0, otherwise we have some energy balance depending on f. But let's assume for a second that f is equal to 0. That's the problem. So here we expect, so if omega is smooth enough, is smooth and decays at infinity, then the integral of omega xt to the power p dx is going to be constant. Right? This is because of the transport structure of the equation, and remember that u is divergence free. So essentially, the expectation is that omega gets rearranged by the velocity field u, and the LP norm is not going to change. So we have a very natural class, and this is true. I mean, the expectation is that this is true for every p from 1 to plus infinity. This is called entropy conservation, and is another conserved quantity. And now, I mean, we have entropy conservation. The expectation is that we can build good solutions, good weak solutions in the class associated to this conservation law. And the natural class is the class of velocity fields in L infinity time L2 space. This comes from the energy conservation together with omega in L infinity time LP space for every p. So we can pick one p between 1 and infinity. So this looks like a very reasonable class to look at. And indeed, it's not difficult to prove that there are weak solutions in this class. It's the very same argument I sketched for the resolutions. So you can regularize the equation, you can solve globally once you get, once you have some more regular equation. And then you can use entropy conservation together with energy conservation to get a priori bounds on the solution and pass to the limit. So, global existence in this class holds. The kind of easy compactness argument works for p bigger than 1. P equal 1 is slightly more delicate. Maybe let me write down the references. This is yeah, Yudovic and Viterma Maida are the first papers doing this. And it can be extended also to p equal 1, but let's consider p strictly bigger than 1 for a while. So there are global solutions in this class, but actually we expect more than just global existence. And let me explain why we expect something more. So our equation, let's pick now a solution with vorticity exactly in that class. L2, L infinity L2 with vorticity in LP uniformly with respect to time. And now let's look at the main equation. It's nothing but the transport equation. When you want to understand the transport equation, the first question to ask is about the structure of the velocity field, or precisely the regularity. If the vector field is Lipschitz, then you can apply the standard Cauchy-Lipschitz theory, and kind of natural to expect well-posedness at this point. But let's check the regularity of the velocity field over here, knowing that our solution belongs to that class. So the differential of the velocity field is given by, we can express it in terms of the vorticity using the Biot-Savart law, is the differential of the gradient perp of the Laplacian to the -1 omega. And this is an order 0 operator, is clearly Calderon-Zygmund. So the expectation is that this object, this differential, belongs to L infinity time LP space, when P is between 1 and infinity, and it belongs to L infinity time BMO in space, when P is equal to plus infinity. Okay, this standard Calderon-Zygmund inequalities. So in particular, when P is equal to plus infinity, the case of bounded vorticities, you get the velocity field which is almost Lipschitz. So when P equal plus infinity, then Q is almost Lipschitz. So you can almost apply the classical Cauchy-Lipschitz theory, and you know that at least the linear problem associated to U is well posed. And this is telling you that the vorticity is essentially transported by the flow of U, which is well defined. So the vorticity at time t is nothing but the vorticity at time 0 composed with the inverse of the flow map. Capital X here is the flow map associated to. So in particular, you can make rigorous the entropy conservation. And you hope for well-posedness also for the nonlinear program. I mean, this is not, this naive argument is not giving well-posedness, but it sounds kind of reasonable. But let's then consider also the case P between 1 and plus infinity. You can no longer apply the standard Cauchy-Lipschitz theory. It is known that trajectories of a Sobolev vector field might be non-unique. But actually there's a theory developed by, initiated by Di Perna and Lyons back in 1989, with a striking contribution of Ambrosio in 2004. And this theory says that if you have a Sobolev velocity field, you can define a generalized notion of flow called the regular Lagrangian flow. And under certain assumption on the integrability of the density, so if you study the transport or the continuity equation, under certain reasonable integrability on the density, the problem is well posed, and you can express the solution to the transport equation in terms of this regular Lagrangian flow and the initial condition. So in particular, under some mild integrability assumptions, even in the case 1p infinity, you can express the vorticity in terms of the initial condition and the generalized motion of flow. You can check rigorously that entropy conservation and energy conservation, energy and entropy, hold when P is big enough, bigger than or equal to 3/2. So again, it looks like the problem is quite rigid, and these weak solutions, at least when P is bigger than 3/2, look like well-posed. When P is equal to plus infinity, well-posedness has been proven. This is a theorem by Judovich. verbosness, I essentially mean uniqueness, existence and uniqueness. There are also other quantitative properties, but I don't want to mention them. So this is Yudovic. If I remember correctly, right from the theorem. So it says that in R2, if you pick an initial vorticity in L infinity intersection L1, you can pick body forces with certain regularity, but for the sake of simplicity, let's put F equals 0. Then there exists a unique solution omega in the class L infinity time, L infinity space with velocity field in L2 time, L infinity time, L2 space. So when t is equal to infinity, you get a unique solution in the class of bounded vorticities. And this is called the Yudovic class. And the case p smaller than infinity is an important open problem and is still open. So our solutions omega in L infinity time, L space with p smaller than infinity unique. Or in other words, is the Yudovic class sharp when it comes to uniqueness? This is not known. It's the second no uniqueness question I wanted to present in this series of lectures. And exactly as in the case of Leray solutions, there's a negative result in the forcing framework. And this is a recent theorem by Ishik. And we reviewed and modified a bit the statement in collaboration with like 7 authors when we were postdoc in Princeton, and we did a series of lectures on the work by Ishik, and we brought down a lecture note about this theorem. And the statement is very similar to the one I presented for the Navier-Stokes equation. So there exists an external body force F, which is L1 in time, L infinity, LT space intersection L1 space, and we fix any p bigger than 2, but smaller than plus infinity. Given p, there exists an external body force F, such that the Cauchy problem dt omega plus u dot grad omega equal f omega 0 equal 0. So again, 0 initial condition, external body force F. That's the Euler equation with external body force F. And of course, Biot-Savart law, u equal gradient perp Laplacian minus 1 of omega. And this problem admits two distinct solutions. Okay. Yeah. Oh, sorry, I should have written Okay? And let me mention another result. Maybe Anush will say something more on Friday. Very recently, using the method of convex integration, we managed to solve this question with zero external body force for a very small range of exponents p. So what we can prove is that this is in collaboration with Maria Colombo and Anush Kumar. What we can prove is that if there exists some exponent p bigger than 1, and actually in our current proof is very small, it's like 1 plus 10 to the minus 5, something like this. Such that the Euler equation with zero external body force, so dU plus u dot gravity in velocity formulation plus MATLAB p equal to 0 admits infinitely many solutions with the same initial condition in the class omega at infinity time LP space in the torus, say 0, 1 times the two-dimensional torus and the velocity field in at infinity time L2 space. But the key point of our theorem is actually the flexibility, and this will be the topic of the last lecture. So those are convex integration solutions. Those solutions are very flexible. We can even build a solution which starts equal to 0, after a while it becomes different from 0, and then it goes down again to 0. So this is no uniqueness, but actually here the key word is flexibility. And these solutions do not conserve the energy, they are super flexible. While the solutions built here are much more rigid. They conserve the energy, and the no uniqueness scenario here is very specific. This is a symmetry breaking type no uniqueness coming out of a very strong form of instability at time t equal to 0. And the instability is hidden over here in the external body force. So next time I'm going to elaborate more on this stronger, say, less flexible no uniqueness scenario, and I'll mainly talk about Navier-Stokes, but the picture is very similar, and in the last lecture I'll elaborate more on flexibility and convex integration. And I stop here.
Thank you very much. More questions? Comments? Yes, please.
Thank you for your time. I was wondering if the result of the spec is not flexible.
What do you mean? F is not very regular. I should have did okay. So again, F is smooth when t is positive and singular only at t equals 0, and is kind of explicit in this construction, and it's actually very rigid. It's rotational invariant. It has a similar structure, so it's a kind of rigid object. And yeah, I don't know what you mean precisely by flexible in this.
I mean, is there no possibility to perturb this F a little bit?
Yeah, this is a good one. You can perturb a bit F, and this no uniqueness and this instability will survive. This is possible, but you have to perturb it in the correct functional spaces. And here again, the key word is critical spaces. All of these phenomena about instability and symmetry breaking are at the level of self-similar solutions that are solutions living in exactly critical spaces. So if you perturb in the current critical space, tiny bit, this picture is going to survive. I forgot to mention, I had a comment for you about your previous question. Here, as soon as p is bigger than 3/2, you have energy conservation for solutions in this LP class. And the question of uniqueness is open, but the expectation is that p equal infinity is the threshold. So here is an example where 3/2 is the threshold for energy conservation, and then there's a huge range of parameters from 3/2 to plus infinity, where you expect at the same time conservation, so you know that conservation happens, but you expect also the uniqueness. And then when p is bigger than plus infinity, you get both uniqueness and conservation. So this is somehow the picture. Yes. I mean, tomorrow's lecture will be entirely devoted to this picture, so I'll try to explain.